Hi, my name is Dr. English, and today we're going to start talking about the trends of the periodic table. Specifically, we're going to look at what the definition is of an atomic radius, the trend of the atomic radius across a period, atomic radius down a group, looking at the definition of an ionic radius trends across a period, ionic radius trends down a group, and finally a little bit of practice at the end. So first of all, what is atomic radius? And the definition of atomic radius is defined as the distance from the center of the atom's nucleus to its outermost electrons contained in the valence energy shell. In other words, you're going from the nucleus, which is right at the very center, all the way out to where the valence electrons would be located. So if we did a Bora model of an element, let's say lithium, and in lithium we know we have 3 protons and 4 neutrons, and that's our nucleus. And we said in our first shell we have 2 electrons. In our second shell we have 1 electron. Then the atomic radius would be going from the center of the nucleus out to that outermost shell where we find our 1 valence electron. Now let's look at the trend of atomic radius across a period. The trend is that the atomic radii of successive atoms will decrease across a period. What that means is that as you go across the period from left to right, the atomic radii of those particular atoms are going to get smaller. Let's look at the explanation why. Moving from left to right, the nuclear charge, which really translates into the number of protons, or your atomic number, and the number of electrons filling the outer principal energy level will increase. This means the number of valence electrons in that outermost shell is increasing as you go across the period, which makes sense. Sodium has an atomic number of 11, magnesium of 12, and aluminum of 13. As you're going across, the number of protons in these elements is increasing, making the nucleus more positive. At the same time as you're going across, the number of electrons in that outermost shell is also increasing, making the outermost shell more negative. If you have a nucleus that's becoming more positive and an outermost shell that's becoming more negative, they're going to attract to each other. And as they attract, the atomic radius is going to get smaller. So if we look at our example down here, here's nuclear charge and here's valence electrons. So for sodium has a nuclear charge of 11 and 1 valence electron. Magnesium is 12 and has 2 valence electrons. Aluminum is 13 with 3 valence electrons, and so on and so forth as you go across the period. The number of protons in the nucleus is increasing while the number of valence electrons in that outermost shell is increasing, and as one becomes more positive and one becomes more negative, they are going to be attracted to each other just slightly, and the atomic radius is going to decrease. Now let's look at the trend of atomic radius down a group. The trend is atomic radius is going to increase moving down a group. And as you can see in this visual right here, they're showing the atoms basically getting larger. Here's the explanation. With each successive element, 1 shell is added to the atom. So you can almost picture here, like in a Bora model, the atoms getting larger and larger and larger as a shell is added after each. Therefore, the radii of the successive atoms increases. So if we look at lithium and we say, okay, here's my nucleus right here, and here's going to the outermost edge. Compare that amount of distance, roughly, to if I had cesium down here, and the distance for atomic radius at the outermost edge there. The atomic radius for cesium is going to be much larger than that of lithium. A further explanation can be seen if you look at Bora models. So the outer electrons of successive elements are farther away from the nucleus. The inner electrons, also known as the core electrons, shield the outer electrons from the pull of the positive nucleus, allowing the radius to increase. So in each of these cases, as we go down a group, there's 3 protons versus 11 protons versus 19 protons. These protons are attracted to the electrons outside in each of these shells. If we talk about the valence electrons are actually shielded here by these inner core electrons. For a situation like lithium right here, there's not much of a shield as there's only 2 core electrons. But something like sodium, if we have this electron, this valence electron in this 3rd shell, it has 10 electrons shielding that one valence electron from the nucleus. And then if we look at the nucleus of potassium, we have the one valence electron in the outermost shell. 18 electrons shield that one electron from the nucleus, so that one valence electron can be much farther away from the nucleus than the core electrons. Now let's talk about ionic radius. When an atom forms a positive ion by losing one or more electrons, the ionic radius is smaller than the atomic radius. When an atom forms a negative ion by gaining one or more electrons, the ionic radius is larger than the atomic radius. What does this look like? Let's start with a magnesium atom. We know in a magnesium atom there is 12 protons and 12 neutrons. And the electron configuration for a magnesium atom is 2 electrons, 8 electrons, and then 2 electrons. So if I count up these electrons, 2 plus 8 plus 2, that gives me 12 electrons, 12 protons. This is an atom. We know that by looking at your periodic table that the only charge that magnesium can be is plus 2 because it's losing these outer 2 valence electrons. So when we draw the magnesium ion, we still have 12 protons, 12 neutrons in our nucleus. Those are not affected. But now my electron configuration for this ion is 2 electrons and then 8 electrons because that outermost shell is lost. And then we put our brackets around the whole thing and we call this plus 2. What we're looking at is the change in atomic radius versus ionic radius. The atomic radius goes from the center of the nucleus out, in this case, to the third shell. The ionic radius is going to be smaller because we lost that outermost shell. So that's going to go from the center of the nucleus, but only to the second shell here. So 1 shell, 2 shells versus 1, 2, 3 shells. So when an atom becomes a positive ion, the ionic radius is going to be smaller than the atomic radius. Now let's look at an oxygen atom. In oxygen, we know that there are 8 protons and 8 neutrons in our nucleus, and that the electron configuration for oxygen is 2 electrons and then 6 electrons. I can double check myself here because 2 plus 6 gives me 8 electrons, 8 protons, neutral, it's an atom. If you look at your periodic table, the only charge that oxygen can be is minus 2. So if we were to draw the ionic radius here, it'd be 8 protons, 8 neutrons in the nucleus. But now my electron configuration would be 2 electrons and then 8 electrons. Now here's the thing, because when I look at this, the number of protons are 8, the number of electrons are 10. I have a charged particle here, a negative ion, overall charge is minus 2. Comparing the atomic radius of oxygen to the ionic radius of an oxygen ion is much more difficult than when you're looking at an atom going to a positive ion. In an atom to a positive ion, it's much more straightforward. You've lost that outermost shell, the ionic radius is going to decrease. In this case, though, going from an oxygen atom to an oxygen ion, my outermost shell is actually expanding. Imagine 2 people that don't like each other. They should be trying to get away from each other. So now we have this valence shell full of negatively charged electrons that have spaced themselves around the nucleus, with 6 electrons being present. If I try to stuff in 2 more electrons, which are negative, to compensate for those 2 electrons coming into that shell and maxing out at 8, that whole shell has to expand a little bit so the electrons can get away from each other. They are going to repel each other. So when you go from an atom to a negative ion, that outermost shell is actually going to expand or get larger. So the general trend here, going from an atom to a positive ion, your radius is going to get smaller. Going from an atom to a negative ion, your outermost shell is going to get larger and your ionic radius is going to get larger. Let's see some data that backs up these trends. Let's look at the trend of ionic radius across a period. The trend is the ionic radius will decrease in a period. And the interesting thing about talking about ionic radius and trends and atomic radius and trends is that basically they're the same. So let's look at the explanation that backs up this trend. The outer electrons of the ions are held more tightly by increasing nuclear charge across the period. So if we start off by looking at this data right here, one thing that you need to keep in mind is that when you look at ionic and atomic radius trends across a period or down a group, you really need to separate them in your head between metals and nonmetals. So if I drew a line right here going across, we could look at these metals and this metalloid and what's happening to here, because all of these atoms, when they become ions, are going to lose electrons. So they're going to lose electrons, and they're all going to have 8 electrons in that outermost shell because they've lost their valence electrons. So the number of electrons in that outermost shell basically stays the same, but the nuclear charge, the number of protons in the nucleus, is getting greater. And as the nuclear charge increases and becomes more positive, it's going to have more pull on that outermost shell, pulling it in. So as we look at sodium to magnesium to aluminum to silicon, we can see that the ionic radius is going to get smaller. Then we start at phosphorus, and phosphorus gains 3 electrons to get that full outer shell of 8. So it's going to have the largest ionic radius, but then with silicon, even though it gains 2 electrons, the nuclear charge increases and the ionic radius gets a little bit smaller, and chlorine gains 1 electron to get 8 in its outermost shell, still increasing nuclear charge, and its ionic radius is going to get smaller. So the general trend that we see, and we can see it on this graph right here, is that as you go across the period, the radius is going to get smaller here as we look at the elements that are becoming positive ions, and the radius is also in general going to get smaller here, again, as we look at negative ions. So whether it's positive or negative, the radius is still going to decrease. Now we're going to look at ionic radius down a group. Ionic radius is going to increase moving down a group. Our explanation: outer electrons of the ions at the bottom of the group are not only farther from the nucleus due to the presence of additional shells, but are also shielded from the pull of the nucleus by the positive-negative force of attraction between the nucleus and the inner electrons. So just like we saw with atomic radius, as those outermost electrons were shielded by those inner electrons, same thing happens here. As you go down a group, those electrons get farther away, whether it's valence electrons or just the outermost shell, and the ionic radius is going to increase. So if we look at group 16, going from oxygen to sulfur to selenium to tellurium, as we go down, the ionic radius increases, and we can see that again in a general trend if we look at our graph right here. Now let's do a little bit of practice. So I want you to stop, read the question, see if you can get the right answer, and then we'll check your answers when you're done. Welcome back. Let's look at the first question. A magnesium atom differs from a magnesium ion in that the atom has a smaller radius, smaller nucleus, larger nucleus. Well, we're talking about the difference between an atom and an ion here. And when we talk about the difference between an atom and an ion, the nucleus is not affected. So that means C and D are both out. Now, in a magnesium atom, we know the electron configuration is 2, 8, 2. And we know in a magnesium ion, which is Mg plus 2, the electron configuration is 2, 8, because it's going to lose that outermost shell. That means that a magnesium atom differs from a magnesium ion, that the atom, not the ion, but the atom will have a larger radius because it has the valence shell while the ion does not. Let's look at the next question. Within period 2 of the periodic table, as the atomic number increases, the atomic radius generally decreases, increases, remains the same, follows no pattern. Well, we know based on the data that we saw that it's not going to remain the same. And we do know that it does follow a pattern as the number of protons increases in the nucleus and the number of valence electrons in the outermost shell is going to increase. So we know the nucleus is positive, we know that the outermost shell is negative, and the nucleus is going to become more positive as you go across the period, and the outermost shell is going to become more negative. They're going to attract to each other. That means the radius is generally going to decrease. So what did you learn in this tutorial? We talked about the definition of atomic radius. We looked at the trend of atomic radius across a period and down a group. We talked about what is ionic radius. We looked at the trend of ionic radius across a period and also down a group. And then we did a little bit of practice at the end. Need more help? Please feel free to contact me. Hope you have a great day.